All right, let's jump right into this explainer. We've got to talk about the massive elephant in the room when it comes to containerized architecture, statelessness. Look, containers are built to spin up and tear down in absolute milliseconds, right? Which is fantastic for scalability, but, well, it creates a pretty huge headache for our data.
Because seriously, what actually happens to your data when a Docker container dies? If you're setting up a database or a file server, that question is literally the stuff of nightmares. Here's why. That writable container layer gets permanently, irreversibly wiped the exact second the container stops. All your hard work, your user data, those configuration changes, poof, gone forever.
So today, we're going on a bit of a problem-solution journey to fix that. We'll tackle the stateless container problem, master Docker volumes, figure out how to share data safely, use host volumes, configure our container environments, and finally define volumes right inside our images. Basically, we're going to learn how to give our data absolute immortality. All right, part one, the stateless container problem. To fully grasp the solution here, we really need to understand the intentional limitations built into that container layer.
Think of that writable container layer like a hot desk at a co-working space. You can spread your work out during the day, but it gets wiped totally clean every single night. If you run a script that creates a text file inside an Alpine container, it lives in that temporary layer. But if you want your changes to survive past the container's lifecycle, you need Docker volumes. These are basically the heavy-duty external hard drives you plug in to save the stuff you actually care about.
Moving to part two, mastering Docker volumes. This is the absolute hero of our story, the ultimate mechanism letting our apps safely consume, produce, and modify state. So what are they exactly? Docker volumes are essentially storage mechanisms managed entirely by Docker, living securely on your host file system. The absolutely crucial takeaway here is that when a container using a volume inevitably dies, the volume and every single byte of data inside it just sits there completely untouched. The data's lifecycle is 100% decoupled from the container's lifecycle. And the best part? Volumes aren't just some invisible terminal magic. You can actually manage and create persistent storage right inside the Docker desktop dashboard. You literally just click over to the Volumes tab, hit Create, and you're done. Super accessible. But under the hood, Docker is pulling off something incredibly flexible. By swapping out volume drivers, you can back your volumes with almost any storage system out there. You've got the default local driver for your regular hard drive, sure, but you also have NFS for network file systems, CIFS for Windows Samba shares, rclone for cloud stuff like Google Drive, and even RexRay for AWS EBS block storage. The container has no clue. It just writes to a folder, and Docker handles all the complex routing behind the scenes. And we can totally prove where this data lives. If you run a quick Docker volume inspect command, it spits out the exact mount point path on your host system. So right here, it's pointing to a specific path under var/lib/docker. That right there is the physical location where your immortal data actually lives. Okay, part three, sharing data safely. Because now that our data is safe from getting nuked, we really need to look at how we share that exact same data across multiple containers. Think about it. How do multiple containers read the exact same data without corrupting it? Say you've got one app constantly writing logs to a volume, and a completely separate container needs to jump in and index those logs. We absolutely have to stop that second container from accidentally overwriting or messing up our shared data. The fix for this is surprisingly elegant. Just slap a colon and read onto the end of your volume mount command. That creates an ironclad read-only guardrail. As you can see here, our secondary Ubuntu container can view the data perfectly fine, but the second it tries to actually change anything, the file system completely blocks it. It is entirely locked out of messing with your state. Moving right along to part four, using host volumes. This is basically the ultimate developer cheat code. Say you're building a website. Instead of setting up a managed volume, you can literally just mount your live workspace folder straight into an Nginx container. You just take your local source code folder, map it over to the container's web directory using an absolute path, and boom, you've just created a magical edit and continue workflow. And trust me, this is a massive time saver. Without it, you'd be stopping the container, rebuilding the entire image, and restarting it every single time you tweaked a single line of HTML. No thanks. With a host-mounted volume, those updates sync bidirectionally in real time. Every time you hit save in your code editor, the changes instantly update on the live server inside that isolated container. Just refresh the browser and you're good. One quick heads up though, because your container is reaching directly into your host system's files, OSs like macOS and Windows are going to throw up a security prompt. It's just asking you to explicitly give Docker permission to read those protected folders. Just click Allow and you are off to the races.
All right, part 5, configuring container environments. Just like our containers need that persistent data to be useful, they also have to be flexible enough to survive dev, test, and production environments. Remember, a container is a totally isolated sandbox. It is walled off from the host. So the environment variables running on your laptop are definitely not the same ones inside the container. That's why we use environment variables. They act as this secure little bridge to deliberately pass dynamic settings, stuff like API keys, database URLs, or log paths, right through those container walls.
And you've got options here. You can throw an N flag right into your startup command for a quick override. But if you're dealing with a complex app that has like 50 settings, doing that inline is going to turn into a nightmare fast. Instead, you can pass a whole collection of them at runtime using an N-file flag. Or, if you're the one actually building the image, you can bake default fallback values straight into the Docker file, so it always boots up with a solid baseline. Which brings us to part 6, defining volumes in images. This is a super fascinating concept. Think about it. What happens if you pull a database image, but the person who built it has literally zero clue how you're going to start that container? Well, maintainers for heavy-duty stateful apps like MongoDB use the volume instruction directly inside the Docker file blueprint. You feed it a path or a JSON array, and it does something kind of brilliant. It automatically forces Docker to spin up a managed volume for that specific folder at runtime. It basically guarantees that your critical database paths bypass that temporary container layer, even if you totally forget to mount a volume yourself. If we poke around inside the official MongoDB image, we can actually see these hard-coded volume instructions in plain text. It lists critical paths for the database config and the database itself. It's built from the ground up to protect you from yourself, basically engineering the application to never ever forget your data by dynamically provisioning that storage right out of the box. And honestly, that is the sheer power of Docker persistence. You've mastered memory using volumes, and you've got the flexibility of environment configurations down perfectly. You've successfully escaped the trap of statelessness. So my question for you is, now that your containers can actually remember things, what massive stateful applications are you going to build next? Get out there, mount some host volumes, set up those environment variables, and conquer your deployments. Thanks for hanging out with me for this explainer, and I'll see you in the next one.